Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Algebra. In today's class, let us solve some of the exercises on dimension of a subspace. In this class, let us first quickly recap the previous concepts which are useful in this class in solving the problems. And in the later part, we solve problems on dimension and problems on dimension of null A and dimension of column space A. With this class, we came to an end of first unit. So let us recap all the important points related to dimension in this class. If these three are satisfied by a set, then we can say that that is a subspace of a vector space. So remaining properties will inherit from the vector space. And linearly independent set, an indexed set of vectors v1, v2 and so on vp in a vector space V is said to be linearly independent if the vector equation c1 v1 plus c2 v2 plus so on plus cp vp is equal to O has only the trivial solution. C1 is equal to 0, C2 is equal to 0 and so on Cp is equal to 0. So if a set V1, V2 and so on Vp of a vector space V is said to be linearly independent if this relation has only the 0 solution. There is no other solution other than 0. And if the set V1, V2 and so on Vp is said to be linearly dependent if the vector equation C1 V1 plus C2 V2 and so on Cp Vp is equal to O has a non-trivial solution. That is, if there are some weights or scalars C1, C2 and so on Cp not all 0 such that C1 V1 plus C2 V2 plus so on plus Cp Vp is equal to O, the 0 vector. So if the set has a non-trivial solution for this vector equation, that is at least one of these scalars must be non-zero, then we can say that the set is linearly dependent. If we can't find a non-zero solution, then we say that the set is linearly independent. And one more important definition is that basis. Let H be a subspace of a vector space V. An indexed set of vectors V is equal to set of B1, B2 and so on BP in V is a basis for H if the two conditions. First one is V is linearly independent set and the subspace spanned by B coincides with H. That is H is equal to span of B1, B2 and so on B. So if these two conditions are satisfied by set B, then we say that B is a basis for H. If we can find a similar set, a linearly independent set which can span entire vector space B, then we can say that that set is a basis for we have seen some of the theorems, proof statements, which can be used in solving the problems and other concepts. This is the one of them. If a vector space V has a basis V is equal to B1, B2 and so on Bn, then any set in V containing more than n vectors must be linearly dependent. And the consequence of the theorem is that if a vector space V has a basis V with n vectors, then each linearly independent set in V has not more than n vectors. So whenever you have a basis with n elements, you can't find a linearly independent set with more than n vectors. And if a vector space has a basis with n vectors, then every basis of the vector space must consist of exactly n vectors. That is, all the bases of a vector space V has equal number of vectors. And with this, we define the definition of dimension, that unique number, the equal number of vectors in all the bases of a vector space is called the dimension whenever it is finite. So if a basis for a vector space V is a finite set, then V is said to be finite dimensional, and the number of vectors in a basis for V is the dimension of V. So that is the definition of dimension, and it is denoted by dimension of V. We write the first three letters, of course. We call it as dimensional. The dimension of the zero vector space, singleton set 0, is considered as 0. And if V is not spanned by a finite set, then V is said to be infinite dimension. It should be infinite dimension. So this is one more statement. Let H be a subspace of a finite dimensional vector space V. Any linearly independent set in H can be expanded if necessary to a basis for H. So whenever you find a linearly independent set in a subspace of vector space V, that can be extended to the level of a basis. And H is also a finite dimensional vector space, and dimension of H is less than or equal to dimension. So every independent set, linearly independent set, can be extended to form a basis for a subspace. And this is one more result. Let V be a p-dimensional vector space and p greater than or equal to 1. Any linearly independent set of exactly p elements in V is automatically a basis for V. And similarly, any set of exactly p elements that spans V is automatically a basis for V. So for a basis, we need two conditions: linearly independence, and it should span the set. Out of these, if the number of elements in the set are equal to the dimension of that space, that is another, that is the number of vectors in another basis, then one of this condition is sufficient, so that that set is a basis for the vector space. And we have seen the definitions of null space and column space. The null space of an m by n matrix A, written as null A, is the set of all solutions of the homogeneous equation Ax is equal to. So Ax, the null A gives us the solution set for the homogeneous equations Ax is equal to 0, or when it is converted into a matrix equation Ax is equal to. And it is denoted by null A. That is, null A is equal to set of x such that x belongs to Rn and Ax is equal to O, the null matrix. Null A is the set of all x belongs to Rn that are mapped into the zero vector of Rn. And null space of an m by n matrix A is a subspace of Rn. And column space of a matrix. The column space of m by n matrix A is the set of all linear combinations of columns of A. it is denoted by column space A. And if A1, A is equal to a matrix of A1, A2, An, where A1, An, A2, An are the columns of matrix A, then column space A is equal to span of A1, A2, and so on. This is the column space. And dimension of null A and column space A can be determined by using these concepts. The dimension of null A is the number of free variables in the equation Ax is equal to O. So if we prepare an argument matrix AO, and null A is the number of free variables in A. The dimension of column space A is the number of pivot columns in B. So non-pivot columns will become, number of non-pivot columns is the dimension of null A, and the number of pivot columns will be the dimension of column space. So these are the things which we have gone through in the previous classes. In the second part, let us solve some of the problems related to dimension. This is one of the problems. For the subspace set of column matrix 2C, A minus B, B minus 3C, A plus 2B. 4x1 column matrix is given, where A, B, C are real numbers. Find a basis and state the dimension of the subspace, given subspace. So let us name the given subspace. Let H is equal to set of column matrix of 2C, A minus B, B minus 3C, A plus 2B, such that A, B, C belongs to R. Then H can be written as, so this column matrix can be written as H is equal to set of A times 0, since in the first row there is no A is absent here, so it is 0, and here there is 1A, so it is 1, and in the third row A is absent, so it is 0 here, and in the fourth row it is 1. So 0, 1, 0, 1. A times 0, 1, 0, 1 plus B times, and here also B is absent, so 0, minus 1 time minus B, so the coefficient of B is minus 1 here, and in the third row it is 1, and it is in the fourth row it is 2. So 0, minus 1, 1, 2 plus C times, here it is 2, absent in the second row, so 0, minus 3C is here, that's why the coefficient of C is minus 3, and in the fourth row C is absent, so it is 0. So the given subspace H can be written in this form, where A, B, C are real numbers. So if these three are our vectors V1, V2, V3, then now H is in the form of AV1 plus BV2 plus CV3, where A, B, C are scalars, real numbers. So we can say that H is equal to span of these three vectors. Here these three vectors are named as V1, V2, V3. So H is equal to now span of these three vectors. Let A is equal to matrix of V1, V2, V3. That is a 3 by, here 4 rows are there. So 4 by 3 matrix is formed using these three vectors. So now let us reduce it into echelon form by performing elementary row operations. So here in two non-zero rows in the first entry, these two are brought as R1 and R2 by interchanging the rows. So I can interchange R1 and R2 first, and later I can interchange R2, R4 and R2 also. So by performing these two operations, I will get this matrix. So using this leading entry 1, I can make it 0. So R2 goes to R2 minus R1. So 1 minus 1 is 0, 2 minus of minus 1 is 3, and 0 minus 0 is. Remaining rows are kept as this. Remaining last two rows are R3 and R4 are kept as this. So now these two rows R2 and R3 are interchanged, so that I can get one here. So by interchanging R2 and R3, I will get this matrix. And using this one, I am making this element 0 and this also 0. So to make this as 0, R1 goes to R1 plus R2, which will give us 1 plus 0, 1. So in this step, I am making this 0. So R3 goes to R3 minus 3R. So 0 minus 0, 0. 3 minus 3 is 0. 0 minus of minus 9 is 9. Now it is in echelon form. So to make it into reduced echelon form, we need to make it also 0. But now echelon form is enough to find the pivot columns. So now this matrix is in echelon form. And clearly we can see that these three are pivot positions. This one and this one and this two. These three are pivot positions. And each column, there are only 3 columns. All the 3 columns are pivot columns. Each column has a pivot position. So all the columns are pivot columns. So V1, V2, V3 are linearly independent, and V1, V2, V3 spans H. Already we have seen earlier that H is equal to span of V1, V2, V3. And now these three, V1, V2, V3 are linearly independent, since all the columns are pivot columns and there is no non-pivot column. Here the third row, this one, does not have pivot position. That implies that the columns does not span R4. That is not required here. So the third row does not have a pivot position that gives us these columns cannot span R4. That is immaterial to us in this problem, of course. So for this problem, V1, V2, V3 spans H, as these vectors are derived from the definition of H itself, and these three are linearly independent. So we can say that set of V1, V2, V3 is a basis for H. Since the basis of H has three vectors, dimension of H is 3. So this is the way to find out dimension of H. And this is one more problem. For the subspace, set of A, B, C such that A minus 3B plus C is equal to 0, B minus 2C is equal to 0, 2B minus C is equal to 0. Find a basis and state the dimension. Let us first name the given subspace as H. That is, let H is equal to set of coordinates all ABC with 3 tuple such that these three relations satisfies. So we need to find order derived ABC such that equations A minus 3B plus C is equal to 0, B minus 2C is equal to 0, and 2B minus C is equal to 0 are satisfied. So we need to find order derived such that these three conditions are satisfied. So these equations can be written in matrix form as this is matrix A. The coefficients of A, B, C are taken here. So it is 1, minus 3 and 1 in the first row, which represents the first equation. 0, since the coefficient of, since A is absent here, so coefficient of A is 0. So 0, 1, minus 2 and 0, 2, minus 1 in the third row. And A, B, C are the unknowns which we need to determine. That should be equal to the 0 vector. That is 0, 0, 0. So this is a matrix equation of the form Ax is equal to O, the null matrix, where A is equal to 1, minus 3, 1, 0, 1, minus 2, 0, 2, minus 1, x is equal to A, B, C, and O is equal to 0, 0, 0. The set of A, B, C, order derived A, B, C are the solutions for the above matrix equation, which is nothing but null space of. So we need to find null space of A, which is H here. So to find the null space of A, we need to find augment matrix. Augment matrix AO is equal to A and all zeros in the last column. So this is the augment matrix. We need to convert it into echelon form first. So this is our augment matrix. So I am making this 2 as 0 by using this 1 by performing elementary row operations. So R3 goes to R3 minus 2R1. So 0 minus 0 is 0, and 2 minus 2 is 0, minus 1 plus 4, minus of minus 4 is plus 4 is 3, and 0. So now it is in echelon form, but to find null A, we are converting this into reduced echelon form. So in reduced echelon form, we need 0 here, and the pivot position should also contain only 1, and there should not any other non-zero element in that particular column, pivot column. So I'm making this 0 again by elementary row operations. R1 goes to R1 plus 3R1 will give me this 1, and this is 1 plus 0 is 1, and this is 0 minus 5 and 0, and I am dividing this with 3 so that I can get this one. R3 goes to 1 by 3 R3. Using this one, I can make these two zeros. So now it is in reduced echelon form. So here, all the columns are pivot columns, and solution for this equation is, if we convert this matrix into equation form, so A is equal to 0, and B is equal to 0, and C is equal to 0. That is the only solution. There is no other solution except A is equal to 0, B is equal to 0, and C is equal to 0. So this is the null solution. So therefore H is equal to 0, 0, 0, the 0 vector of R3, so which we usually denoted by O. So singleton set O. So this is the zero space. There is only one vector, zero vector, that itself is a vector space, of course. So it is the zero space. So since there is only one vector, that is also a zero vector. So the dimension of zero space is 0. If it is a non-zero vector, we can say that that's the dimension of H is 1. That vector can produce many vectors, of course, if that is a basis. But here it is a zero vector, it can't produce anything except that zero vector. So the itself, zero vector itself, the set of 0 or O is the basis for H, and its dimension is 0. And this is one more problem. For the subspace set of A, B, C, D such that A minus 3B plus C is equal to 0, find a basis and state the dimension. So let us name it as H. That is, H is equal to set of A, B, C, D such that A minus 3B plus C is equal to 0. We need to find A, B, C, D such that the equation A minus 3B plus C is satisfied. So we need to all such entries A, B, C, D. So this is 1 by 4 and 4 by 1. That should give us only 1 by 1, 0. This is the null matrix for this equation. So this matrix, this is a matrix equation of the form Ax is equal to O, where A is equal to 1 minus 3 1 0 and x is equal to ABCD and O is equal to 0. 1 by 1 matrix or a scalar. So this set of ABCD are the solutions for the above matrix equation, which is null A. Again, so we need to find null A. So this is the augment matrix AO. 1 minus 3 1 and 0 0. This is our augment matrix, but it is already in echelon form. Since there is only one row, it is already in reduced echelon. So we need to take the equation. That is again A minus 3B plus C is equal to 0. Of course, we need to, we can skip this process. We can directly convert this equation into A is equal to 3B minus C. But as a procedure, these steps are to be followed. So any other problem can be solved in this manner. Even it looks a little bit different from our regular order. So for that convenience, I have taken all these. Otherwise, I can directly write it as A minus 3B plus C is equal to 0 implies A is equal to 3B minus C. So now after converting that into regular matrix form and converting and finding that it is already in echelon form, it is echelon form. I am converting this to A is equal to 3B minus C, which can also be done directly. Here, my intention is not to solve this problem, to solve any type of such problems. That is the case. So now, the matrix A, B, C, D can be written as A can be replaced with 3B minus C. And there is no information about B, C, D. So B, C, D are kept as B, C, D. And I have a relation between A and B, C. That's why A is kept as 3B minus C. So here now I can find three free variables B, C, D. A is dependent on B and C with this relation. So this is equal to B times 3, 1. In the first row, it is 3 times B, so it is 3. And in the second row, 1B. And remaining 2 are zeros, since B is absent. Similarly, this is C times minus 1, 0, and 1, 0. Plus D times 0, 0, 0, and 1. Since B is absent in the first 3 rows. So now these 3 vectors can span our null A. So null A is equal to span of these 3 vectors 3, 1, 0, 0 and minus 1, 0, 1, 0 and 0, 0, 0, 1. So H is equal to span of these 3 vectors again, and we can see that these 3 vectors are linearly independent. Since one is not a, since in no vector is a linear combination of preceding vectors. First vector is non-zero, second vector is not a multiple of first one, and the third vector is not a linear combination of these two. Since you can't get this one with any linear combination of these two, with these two zeros. So these three are linearly independent, which can be seen easily. So these three vectors is the basis for H. This is one of the bases, of course. Is a basis for H. So since there are only three vectors in the basis, you can say that the dimension of H is equal to 3. This is one more problem. Find the dimension of subspace of all vectors in R3 whose first and third entries are equal. So we need to take a subspace whose first and third entries are equal, and that should be a subset of R3. So since it is a subset of R3, there will be 3 entries. If we write it as a column vector, it will have 3 rows. Since the first and third entries are equal, so if first entry is X, third entry is also X. Second entry may be different from this X. So if we name the subspace mentioned in the problem as H, then H is equal to set of column matrices X, Y, X such that X, Y are real. And this can be written as X times 101. So here X is taken out. 101. X is absent in the second row, that's why it's 0. And Y times 0, 1, 0. Since Y is absent in first and third rows, such that X, Y belongs to. Now, if these two are my vectors V1 and V2, then I can say that H is span of V1, V2. So these two vectors can span H. H is equal to span of these two. Here we can clearly observe that these two are linearly independent. Since one is not a multiple of other. So these two vectors can span H and they are linearly independent. So these two vectors form a basis for H. So the set of 101 and 010 is a basis for H. Okay. It should be A, not D. Since it is not there are many bases, many such bases. This is not a unique basis. There will be many more such bases for H. So this is a basis for H. So since there are two vectors in a basis of H, so dimension of H is 2. This is one more problem. Let H be an n-dimensional subspace of an n-dimensional vector space V, then show that H is equal to V. Given that V is an n-dimensional vector space, that is dimension of V is equal to n, and H is a subspace of V, and the dimension of H is also n. This is all the given hypothesis. Suppose H is not equal to V. Now to show that H is equal to V, let us assume that H is not equal to V. Then if H is not equal to V, then there exists at least one vector X in V such that X is not in H. So there will be at least one vector outside of H. Let that be X. So X is in V but not in H. Since dimension of H is equal to N, H is a subspace of V. There exists a set S with n vectors V1, V2 and so on Vn that spans H. So since H is a subspace, it must have a spanning set. Let S be that spanning set. And since dimension of H is equal to n, that spanning set must contain exactly n vectors. That is, H is equal to span of S. Since X is not in H, X does not belong to span of S. So you can't span X with those vectors. If you can span X with those n vectors, then X is in H, but it is not the case. So X is not a linear combination of those vectors, so it is not in span of S. So let us form another set S dash, that is S union singleton set X, that is equal to set of V1, V2 and so on Vn X. X is added to S. Now this set is linearly independent set with n plus 1 vectors. Since the first n elements are linearly independent, since it's a basis, and now X is not a linear combination of those vectors, so even if we add X to that set, it is still linearly independent. But this is a contradiction to the fact that dimension of V is equal to n. Since if dimension of V is equal to n, then there should not be any linearly independent set with more than n vectors. But here these are all the vectors of V and linearly independent, and they are more than n vectors. This is a contradiction to the concept of dimension. So this is not possible. So H must be equal to V. So H is the entire vector space. So that means whenever you are finding a proper subspace of a vector space, the dimension must be less than the dimension of. If the dimension of each dimension of both the subspaces are equal, then those subspaces are equal. Whenever one is a subset of other. Let us quickly go through these problems of finding dimension of null A and column space A. So determine the dimensions of null A and column space A, where A is here. So this matrix A is directly in echelon form. So here we can find that the first column and second column and this fourth column, 1, 2 and 4th columns are pivot columns, and 2 and 5 are non-pivot columns. So as there are 2 non-pivot columns, the dimension of null A is 2, and there are 3 pivot columns, the dimension of column space is A is 3. Similarly, in this problem, this is a 4 by 7 matrix in which 1, 4, this is 4th column, this is 5th, and this is 7th. 1, 4, 5, 7. There are 4 pivot columns and 3 non-pivot columns. 2, 3, and 6. 3 non-pivot columns, so dimension of null A is 3. 4 pivot columns, so dimension of column space A is 4. And similarly here, it is also in echelon form. So 1, 3, and 4 are pivot columns. 3 pivot columns, so column space, dimension of column space A is 3. And 2, 5 are non-pivot columns, so dimension of column space is 2, dimension of column space is 3. So if the given matrices are in echelon form, we can directly find out the null space A and column space. So this is the first unit. With this, I am concluding this class. Thank you for watching.